this evening we're going to have a lecture from Professor Steve Haake. Steve is Professor of Sports Engineering at Sheffield Hallam University, and he's also Director of Engagement at the Advanced Wellbeing Research Centre. And this is an organisation that aims to take technology from sport and to use that technology to enable ordinary mortals like me and you probably to become more active. But actually, Steve is an escaped physicist. Like quite a lot of us, he's gone over to the dark side of engineering. So his first degree was in Leeds, and he read physics at Leeds, and then did a PhD in University of Aston. And I think by then you were heading more towards the engineering end of things. And in 2020, he was made an OBE in the Queen's Honours List for his services to sport. So it gives me great pleasure this evening to introduce Professor Steve Haake. Steve, away you go.
Thank you, Maria. So I just want to check, can you hear me? Maria, can you hear me? Nope, nobody can hear me.
Yes.
You can hear me. Okay, yes. Good. Thank you for the introduction. I'll tell you what, I shall share my screen. Actually, you're going to have to allow me to share the screen if you don't mind.
You should be able to now.
Yeah, brilliant. Okay, right, away we go. Okay, I'm just going to just move around the images. I don't think you've ever noticed when you're doing a zoom that one of the things that happens is that you end up with a little picture of people on top of your PowerPoint presentation, which is really, really annoying. It's all right, let me just play this again. So speaker, share my screen. And the other embarrassing thing is all this is being recorded. So it shows my abilities with this as well. Right, okay, I think I am ready to go, hopefully. Thank you. The impact of technology on sporting performance. Maria, thank you for the introduction. As was just said, yes, I am an escaped physicist. So physics at Leeds University. I then had to, I suppose, get a job. And back in the 1980s, I think a lot of people on this call might not know about the 1980s, long time ago. But the jobs all seem to be in the aerospace sector, and it was all about smart bombs and killing people. Star Wars was in the ascendancy, so there's some very strange jobs going on. This is my way of getting out of that particular sphere, was going to look at the physics of sports, which is what I called it at the time. So today I'm going to take you through a rapid kind of review of the physics of sport and my journey of the last 40 odd years from physics into engineering, and where we're at now in kind of well-being, I think. And hopefully it'll interest you, and hopefully give you some idea of maybe jobs and careers for the future. So this is my research centre. This is the Advanced Wellbeing Research Centre. So this was funded out of a grant from the government that I secured in 2015. And in there, we've got experiments a bit like this. So these are just some of the sports experiments that we do. So here you can see what we have here is we've got a crash test dummy down there. Here we've got 2 rugby players, and actually we're doing some work on studs. So there's a British standard for the shape of studs. And the reason for that is so that you don't get lacerations during a ruck when you're playing the game. So there is a standard for those, and we were looking at how those standards perform, etc. And we're looking at accelerations and forces in that crash test dummy there. You can see we've got this kit everywhere. There's cameras, there's lights, there's action. So it's a really great set of experiments. Quite difficult to do well, but very exciting to do. So here's a question. How can we use technology to improve performance? What technologies do we use in sport? Do they work? And the key question, is it cheating? I get this one all the time. So I thought, okay, I'll throw it up at the beginning and we can talk about that again at the end. So you'll see down here, advantage play, and that's the title of the book that I wrote about all of this, which I'll share at the end. And it's a really interesting phrase, advantage play, a method of gaining a legal advantage during gambling, for instance, wearing sunglasses while playing poker. So advantage play is this kind of phrase that says it's kind of cheating, but not cheating. It's understanding what the rules are and pushing them to their logical extent. You've got to be a little bit careful by doing that. So there's one of the Kardashians wearing a nice pair of sunglasses during poker. You've got to be careful. Mirrored sunglasses don't work very well because as soon as you hold the cards up to your glasses, everyone can see what you're playing with. So you've got to be quite careful the way you do these things. So the first sports technology, I was kind of interested to know if I could find what was the very first sports technology. And you have to go back to ancient Greece. And I found out that there's a recreation of one of the ancient games. So this is kind of one of the grand slam events of ancient Greece. So you might have heard of Olympia and the ancient Olympic Games. Well, also there was three others on top of that, and there's one at Nemea. And I found out that they recreate it every 4 years. So I went along to have a look. And this is what you find. You find a 2,500-year-old stadium set up for the locals to have a little bit of their own little Olympic festival. So you can see there's lines to show on the racetrack to demarcate the runners. You can see some runners on there. And I'm going to show you this little video now. And what you're seeing, this guy here, he's pulling up this pole. And he's pulling it up, and he's putting a little catch on it there. And there's a catapult in here. So about 2,500 years ago, the ancient Greeks invented the catapult. They realized they could fire rocks at people over long distances. And someone said, you know what? In our new running events, why don't we use a catapult to create ourselves a gate? We'll put posts along here for the runners to stand between. We'll put a sill, we've got a sill here for them to stand in. They've got to have their toes in these grooves here. And then we've got someone back here, they'll pull a rope, that'll fall down, and away we go. So here's the recreation of it. So the catapult goes down, and away they go. Just have a look at this guy. I kind of love this guy here. He knows he's not going to win. There you go. Woo! Hands in the air. So what we have there, that's the very first piece of sports technology. And it's a repurposed piece of technology from the art of war to the art of sport. Now, we might think, okay, how ridiculous. But if we fast forward to 1896, which isn't all that long ago in comparison, you actually see things hadn't changed all that much. Here you've got a rough soil track, a cinder track, and that was similar to what they used in ancient Greece. There you can see the posts. We just don't have this starting, but in fact, if anything, we've gone backwards. This starting line is terrible in comparison to the ancient Greeks. What we can see, you can see these different starting poses, and you might be able to guess which one of those went on to win. Who do you think has got the best starting pose there? This is the one that's kind of most modern. That's Thomas Burke. He went on to win that particular first 100-meter sprint at Athens 1896 in 12 seconds. Going up 40 years later, okay, again, things haven't got that much better. We're still on a sandy cinder track. This is a really soft track. Now, this is Berlin, 1936. This is Jesse Owens. For the older ones there, you'll know who Jesse Owens is. So this is Jesse Owens here, over on the right. He won the 100-meter sprint here in 1936. This was the Nazi Olympic Games where Hitler wanted to showcase how Germany was the best at everything. But Jesse Owens turned up and ruined that for him. So again, technology hadn't really moved on, and what you might have been able to see there was Jesse Owens was actually digging a hole in the ground as a foot to push off, creating his own kind of starting blocks. Finally, you get to somewhere like London 2012, a beautiful, beautiful picture, and you can see we have these starting blocks. We now have a hard track, and we can see these athletes all pushing off. The force vector, almost all the same, pushing off from these starting blocks, which are tangential to the angle of the foot to maximize their takeoff. So that first piece of technology is really the starting gate on the most simple of sports, which is the 100-meter sprint. Going back to ancient Greece, so that's the first technology I could see. So what about the very first piece of sports equipment? And the first piece of sports equipment I could find was actually this, which was jumping weights. Right, I'm going to go to my my shelf of delights back here. I've got lots of things here in my office. And here what you can see is I've got two metal weights, and you can see they've kind of got hand grips in there. So these are a modern invention designed and built by a colleague of mine who wanted to go into business selling these things as hand weights. Now, the ancient Greeks and the Romans used these to try and help people jump a little bit further. And you can see here, you can see the coach, he's got a big stick. So his method of teaching people was to whip them if they got it wrong. So there you've got an athlete running. You can see jumping rather, and you can see they've got these weights out in front of them. And the idea is that as you take off, you swing the weights out, and then you perhaps throw them back to you, a bit of momentum exchange. So while you're in the air, you throw them behind you and you land a little bit further. I'm not entirely sure that was actually true because I've tried it. It's really hard to do. But really, it's this: if you were to jump a standing jump, you know what you do, you throw your arms out in front of you. And some experiments have shown that actually using these weights can just increase the force on takeoff. And if the force on takeoff is increased, then you can jump a little bit further. Now, the designs, interestingly, there was lots of designs, contemporary designs. And I think effectively, this early sports technology, people were choosing the piece of technology was best for them. So this is a flat lead bar, and you can see with the bits hanging out ahead, and that increases the rotational moment of inertia, which I'm going to come back to in a little bit. This one here is probably a cheaper model. Lead would have been expensive. This is a stone thing. All you have to do is carve out some finger shapes, and you can start selling them on the street to athletes. So that's the first piece of equipment technology I've managed to find. And you can see these in the British Museum. You go down to London, you can see these. That's a picture from one of the vases in the British Museum in London. So if we look at modern technology, and here is Serena Williams with a modern tennis racket. I mentioned moments of inertia a minute ago, and the ancient Greeks, whether they knew it or not, had been using the concept of moment of inertia. And I've got a couple of tennis rackets back here. And so if you're my great age, you will have learnt with one of these. This is a Dunlop Max Ply. This was on sale for about 50 years. It didn't change very much. So from the 30s to the 80s, this was the top technology in tennis. And you can see here, you can see a modern carbon fiber racket. It's a lot lighter, it's a lot bigger, it's just nicer to play with. So modern technology in sport really started in about the 1870s in the Industrial Revolution. So this was tennis. Before then, it was real tennis. It was played indoors. If you go to Hampton Court, you can actually go and see one of these. There's one at Cambridge University as well. There's only about a dozen of these tennis courts left in the world. But very quickly, about 1865, someone invented the concept of lawn tennis. So the rising middle classes were starting to love their gardens. They started to mow their lawns. They wanted games to play, and lawn tennis was one of those. So here's some very old tennis rackets. You can see this one's looks like it's warped and it's a bit bent. Actually, the reason for that is because it came from indoor tennis that has corners on it. It had a funny shape on it, so you could scoop the ball out the corners. because you're allowed. It's a bit like a cross between tennis and squash, this game. So if we move on, so what we've got, the rackets in the 1880s made out of wood. Here you've got a 1920s one, actually one of the first metal rackets. And here you have the Dunlop Max Ply, which is the one I've just shown you there. They're all pretty similar shape. And what limited the design of this was the material. So it was made out of wood. Effectively, it's a single piece of wood, goes all the way around there. It gets steamed and bent, and then you put some wires around it, you put a handle around it, and there's a kind of a little V-shaped insert there that goes in between the two pieces, one piece, and then you kind of polish it, make it nice. And what limited this racket was that once you strung it, if you made it too big, the whole thing would just collapse. So this was about the maximum size you could make a tennis racket once you'd strung it. We get to 1976, and there's a man called Howard Head. He worked at Prince, and he patented this tennis racket, and he patented the sweet spot of the tennis racket. And he realized that there was a place on the racket where you got the maximum velocity of the ball bouncing off it. And actually, he realized it was quite low down. So what he did is he just made the racket bigger. And the reason he could do that is because this is made out of aluminium. That was stronger. You could make the head bigger and it wouldn't collapse. So he got a patent on this, surprisingly, you know, a bigger headed tennis racket. He got a patent, and then suddenly the whole world of tennis changed. And here you've got another bigger tennis racket, and things went on from there. So I'm going to show you some graphs. Okay, so no physics lecture would be good without some graphs. So the first, what we've got here is we've got date along the bottom. So 1870 up to 2020, this piece of work. And so I worked with Luca Tabarelli here, continue a piece of work I did about 20 years ago, where we went to the Wimbledon Museum, we went to the International Tennis Federation, we said, look, give us all your old rackets, we want to analyze all these old rackets. And we got to play with some rackets that were right back from the 1860s, really, really early on. And what you see is, in terms of mass, the mass of these rackets was all pretty similar, about 360, 370 grams. So there's the kind of average there. You've got a bit of leeway, depending on what they were made out of and so on, but roughly about 360, 370 grams, until you get to these new materials, and suddenly the mass drops down to about 300, and sometimes you're getting 250, and sometimes you're getting just over 200. Now, the problem, you don't want to go too light, because of course it's about momentum exchange. So you've got a ball coming in, you're going to hit it. If this thing is too light, this is not going to be an efficient exchange of momentum. So you can't have this racket too light. So there is a kind of a lower minimum where it works. Then we've got something here called estimated transverse moment of inertia. Now, don't worry about it, it's in kilograms meters squared. What that effectively is the moment of inertia of the racket when you rotate it in this direction. So inertia, just to remind you, inertia, okay, if something is stationary, it's not going to go anywhere until you apply force to it, like that. Rotational moment of inertia is it's not going to rotate until you apply a torque to it. So the moment of inertia is the rotational equivalent of the mass moment of inertia. So what you see is you've got the older rackets, they've got a certain moment of inertia, and as you get to these new rackets, suddenly that moment of inertia drops quite rapidly. This racket is suddenly much, much easier to swing than these old tennis rackets. And I was there, I can tell you it's absolutely true. This is so much easier to play than with this. So to be able to swing this racket is so much easier. And so much easier, in fact, that actually, when I learnt with this racket, okay, I'm going to be careful, I might smash the lights here. When you played tennis, you would kind of face the player and you would turn like this, and you'd have to turn like this. Now what players do is they take the racket, and what they do is they kind of swat like this. It's so light, they don't have to do the old-fashioned turn to make the shot. Just like to draw attention to this one. So that's the transverse moment of inertia. This is the polar moment of inertia. So that is the moment of inertia in this direction. How easy is it to actually twist in your hand? Now that's important, because if you hit a ball right on the center, that's fine. It's not going to twist in your hand. If you hit it off center, it's going to apply a torque at your hand and it's going to make it twist like that. Now, the higher the polar moment of inertia of this racket, if you make it really, really wide and put all the weight around the outside, then it's not going to twist in your hand and it's going to make the game easier to play. And that's what you see here. So you see here the polar moment of inertia start to increase. So what's happened is these rackets have made it easier to play. Now, in terms of elite sport, it's made it easier to play, but elite athletes are all very similar. So they've all increased the same amount. When it comes down to people like me, it's either being able to play or not being able to play. And this really improved things that the people could play. I'll just show you some images here. This is a very early set of experiments we did here. So here's a ball being fired at a racket. Now, when it comes down to doing experiments, physics experiments on sport, doing them outside in the laboratory, outside on the court is really, really hard, because you've got to track the racket, you've got to track the ball, you've got to do it outside, it might be raining, you've got to get the athletes to do the same thing every time. But actually, what's nicer if you do it in a laboratory, and really the momentum exchange is the same, it's just a different frame of reference. Whether you swing the racket towards the ball or fire the ball at the racket, it's exactly the same impact. It's only a frame of reference that is different. So in terms of technology of sport, this kind of shows you one of the key things. It's about a momentum exchange. There's some kind of conservation of momentum going on. So the ball hits the racket moves back, the ball rebounds. The energy in there is all more or less the same. You lose a bit of energy in the impact because there's a bit of sound. The ball heats up a little bit, the racket heats up a little bit. But in terms of that little square, there's a conservation of energy going on. I'll show you the next one. This is a nice impact here. So you've got the ball coming in, hitting on the racket, hitting the racket. And what we're trying to do is we're trying to allow the athletes to have the optimum amount of energy going in. So if you can make this light and get the racket in the right place at the right time at the right speed, then that's going to get energy coming in. And you want the ball to fly off with as much kinetic energy as possible, i.e., that is, high speed. Just show that one again. Now we did kind of cheat with that ball, that tretorn there. It was a punctured ball, which is why you can see in that ball a certain amount of momentum of the back of the ball. So as at the back of the ball, as it hits the racket, the front of the ball is starting to rebound and the back of the ball is still going forwards, which is why you get this funny pancake look of it. Yeah, let's try again. Bam. You can see that back going in as the ball comes out. And that's a very inefficient impact. So when those balls get punctured or they lose the air pressure inside them, and they're very bad to play with because you get very large deformations like that, which are very inefficient. So I'm going to rapidly leave the dynamics there and we'll go on to fluid dynamics. So, okay, swimming, one of the obvious fluids. So air is a fluid, water is a fluid. We'll start with water. So this is swimsuits from about 1890s. We've got a picture here, which I happened to be at the Victoria and Albert Museum yesterday. That's in the V&A, and that's a similar swimsuit for a woman. And it was basically a dress with these things, I think they were called bloomers, not really conducive to performance. And it was the first time performance was really considered when this woman came along. This is about 1906, and she's a woman called Annette Kellerman. And she said, forget those dresses. I'm not wearing those dresses. I want to swim fast. I want to swim the Channel. I want to swim the Thames. I want to break some world records and so on. And so she designed for herself this rather lovely full piece bodysuit. She didn't actually have it as a full piece initially. She had to add the leggings in because when she went to swim in front of royalty, they said, okay, it's a bit risque. You know, you've got to cover yourself up. But she created this wonderful swimsuit. I'm going to come back to that. So she was the first to come up with that as an idea, and that's about 1905. Here we get to about 1908, and actually in terms of performance, swimmers had realized you weren't going to get anywhere swimming at the Olympics with these. This is the 1908 British Olympic relay team, women's relay team. And what they're wearing is they're wearing silk swimsuits. Now, the problem about silk swimsuits is they do go a little bit see-through, and I just love the look of the chaperone's face here, and just looking daggers at anyone that might be looking at them. As we go forward in time, we get to the 80s, and here we have two American athletes, this is Mark Spitz, and oh, I've forgotten the lady's name, Barbara, somebody. I'm sorry, Barbara, I can't remember your last name. And what you can see is you can see that the swimsuits are getting smaller and smaller and smaller. And actually, you can probably see that the skin also is starting to get more and more shaved. So the idea behind fluid dynamics here was, okay, how can we reduce any skin friction as we're swimming through the water? Because it's the skin friction that's going to slow us down. So we don't want to waste any energy moving through the water. We need to be as slippery through that water as possible. So this was the 80s. You had these swimsuits where the cut got smaller and smaller. And this was like kind of the what we ended up calling Speedos, these kind of tiny, tiny briefs. We get to 2000 and things are starting to change. So we've gone from an Kellerman with full body suits. We've got smaller and smaller and smaller and smaller and smaller and smaller, and they're starting to get bigger again. So here we've got Speedo again with some of these suits. And this is the Australian relay team. I think they've just won the gold medal in Sydney 2000. This is Ian Thorpe, whose nickname was a Torpedo because he was so fast. And you can see we've got quite a mixture here. Here we've got some shorter versions of swimsuits. I think they've pulled them down. I don't quite know what the upper torso looked like. Here you've got one without any arms, and here you've got Ian Thorpe with almost a full body suit all the way down his arms. So there wasn't a consensus for what was good, but people were starting to toy with the idea of having full body suits again. And hopefully you can see this video. So this is a video of a swimmer in a swimming flume. So this is a swimming flume over in Germany that I was at doing a documentary. And so you've got the swimmer swimming along, and it's great because it's basically a water treadmill. So the swimmer stays stationary and the water goes past. Basically, there's a big pump and the water goes underneath, down a pipe, out the other end, through a nice filter and goes out the back. So let's just show that again. So the swimmer's actually dived in, coming up, and you can see with the water bubbles where the water leaves the body of this particular swimmer. Now, there's different elements of drag that slows this swimmer down. So you've got wave drag, that's the first thing. So at the head there, you can perhaps just see some ripples. So you've got some wave drag in there. So that's why a hat is really good. Start again. And then you've got bluff drag, body drag, and that's proportional to the area of the swimmer. So, and that's where you get behind the feet, you get a large wake. The larger the wake behind you, the wake shows you how bad the drag is. If you've got a large wake, that's really bad. So where the water leaves the body of this athlete, if you end up with a large wake and lots of turbulence, as you can see there, then that is bad. So that's the second portion. And that's kind of most of the drag. And the idea there is you reduce this cross-section layer that's hitting the water, that's gliding through the water. And if you have legs that slip down into the water, that's not bad. So you can see that athlete is really quite horizontal. The last thing you can see is you can see that this swimmer has got a swimsuit which is kind of quite shiny. So play that again. And this shiny swimsuit has a material on it which is hydrophobic, which repels water. And the final piece of this jigsaw is that the water the suit has some friction to it, and you have a layer of water in contact with that body, The bigger the body, the longer the swimsuit, the more that skin friction. So you're trying to reduce that as much as possible with the materials. So we get to about 2008. Here is Michael Phelps, and he's got this Speedo laser racer, LZR racer. And this swimsuit, almost full body, not the arms. But what you've got is you've got these black bits are made out of lycra, the kind of really stretchy material that you might have in clothing. And here you have some polyurethane material, and that's really stiff material. It's basically a plastic bag. This is the bit that's hydrophobic, has very low skin friction. And this kind of, these panels of lycra here allow you to get the swimsuit on, give you a bit of stretch so you can actually put the thing on. And times started to get really, really short. Times kind of were decreasing rapidly. We get world records all the time. And we get to 2009 world records, world championship, shall we say. And we have, there's Michael Phelps, and he's looking daggers at this person here. And this person is Paul Biedermann, and he's a German, and he's just beat Michael Phelps in the 200 meters freestyle by about a second. Now that's a lot. Usually world records, you're beat by like 100th of a second. So this is 100 times as big as a normal winning margin. And one of the reasons is, can you see his swimsuit? You can see it's hydrophobic. You can see that the water is not really attaching itself to that swimsuit. And there's the lycra bit. All the rest of it is made out of this polyurethane. So that polyurethane is hydrophobic and has a massive advantage for Paul Biedermann over Michael Phelps. I don't know why Michael Phelps didn't wear a full body suit, but he didn't. And this is what happened to the speeds over time. So here we've got 1988 up to 2020. Here we've got swimming speeds. There's the 50 meters. And this is where these swimsuits started to get introduced. 2010, they were banned. And so you see the times drop down again. So it's a great way of finding out if a sports technology works or not by banning something. So you can see it when it's introduced, and then when it bans, take it away. Okay, there you go. And you could almost cover that up, and that would just be a constant improvement. And that constant improvement is there because the athletes are getting better all the time. We're finding better athletes. They're getting better in terms of coaching and training and so on. There's the 100 meters. There's the 200 meters freestyle. And can you actually see these peaks get smaller and smaller as you get to the longer and longer distances? And one of the reasons for that is because these are really, really tight, these swimsuits. So actually they're a bit fatiguing because they impede blood flow. So on these longer distances, they're not quite as good at improving performance compared to these, which are basically an aerobic, explosive, single length of the pool. So there's an example of technology working and it being allowed and not being cheating because the rule said you can do it, and suddenly a rule being introduced and now it's cheating. You're no longer allowed to do it. So, of course, another fluid, excuse me, let's take a drink. So here we have Victoria Pendleton. The older people on the call here will perhaps recognize Victoria Pendleton. And we were asked, if I go over to my shelf here, to look at different helmet designs for the Olympics. Which helmet would be the best one to wear? Now, it's very difficult to do an experiment for someone on track because the differences are really quite small. So we use a thing called computational fluid dynamics. And here we've got a subject, and he's wearing one of these helmets here. So I'm going to stick that on just because I can. So this is actually Victoria Pendleton's helmet because it's got VP written on it on the inside. And here we have the helmet, and what we've done is we've scanned with a laser scanner this athlete into our computer. We've scanned this particular helmet, and we've scanned all the other helmets we looked at as well. And we've now put some airflow over this computer generated model to see what happens. And we've got that in the kind of the cruising position. So you've got on the seat, on the bike, and you've got Victoria or whoever else on the bike like that. And what you can see is you can see the streamlines going down this point and down the back of the athlete. And you've got very little separation, the smallest wake you can possibly have of the fluid flowing over the athlete. If we look at this is a starting position for that particular event. So you might be looking down on your pedals, you might be pushing off in the velodrome as hard as you can. And of course, what you've got is you've got this thing sticking up in the air. And what we found was that actually this is a really bad thing to do. You can see the size of the wake there. It's a huge wake. Now, luckily, that's at the beginning of the event where speeds are really, really small. So it doesn't have quite so much effect. It would have a much bigger effect later on. So what you'll see now is if you look at the Olympic Games and you look at some cycling events, what you'll see that they have chopped off the back of these helmets most of the time, because in that orientation, they're not advantageous, whereas in that way, they are advantageous. So it's the same principle as we had with the swimsuits, that there are certain things which which are proportional, that increase the drag, shall we say. So drag, aerodynamic drag, hydrodynamic drag is proportional to the area presented. And you can see there's large area. Look at the previous one. There's a small area presented. So that's the first thing. So the area is quite small. It's proportional to the density of the fluid you're going through. So whereas with air, it's roughly 1 kilogram per meter cubed. With water, it's about 1,000 kilograms per meter cubed. So 1,000 times the density, 1,000 times the drag when you're going through water. And then the other thing is the drag coefficient. So the drag is proportional to drag coefficient, and that's the efficiency of the air flowing over these suits, over these helmets. And we can manipulate that by putting all sorts of funny little dimples on here. And you might have heard of the dimples of the golf ball. The whole point of the dimples on a golf ball are to reduce the drag coefficient and reduce the drag and let the ball fly further. Here we have a full bike computational fluid dynamic model created by John Hart at Sheffield University. And we've got a Planet X road bike here. We've put in the whole bike, all the components, the spokes, and a road helmet here. And we're just pulling the air up through here to work out what the different drag is of all the different components. Because it's a computer model, we can isolate any components, and we can change the components, and we can reduce that drag. It's exactly what we do for our Olympic teams. And we can do it for other events. So here we've got wheelchair racing. Again, you're flying through the air. And what you're trying to do is you're trying to maximize the energy input by the athlete. And the athlete in wheelchair racing pushes on these rims here, and minimize the energy loss, which is the aerodynamic drag due to the chair and the athlete. And in this particular model, what you find is if we take that person apart, what you find is the athlete represents about 58% of the drag, the wheels is about 17% of the drag, and then the other components is about 25% of the drag. So actually getting the athlete in the right position is going to have the biggest bang for your buck, but you can actually have quite a large impact if you redesign the wheelchair itself, and perhaps do something about the wheels, because the wheels are quite messy if they've got spokes rather than kind of being full panels. I don't want to leave this kind of material kind of equipment part without mentioning shoes. And if we go back to Jesse Owens in 1936, so he's running on this cinder track. You can just see him there. That was his starting blocks. He'd kind of dug it out with a little trowel that he could push off against. And there's his shoes, made out of the materials of the time, which was leather. These are Adidas shoes, actually. So Jesse Owens was American. It was 1936. Germany was just about to go to war. Adidas was a German company. And Adidasler, who is the originator of Adidas, sent Jesse Owens a pair of his shoes. And I think unbeknownst to Hitler, Jesse Owens ran in Adidas shoes. And afterwards, Jesse Owens sent him the shoes back with a little thank you letter saying thank you for the shoes. And he sent the shoes back. And I've seen these in the Adidas Museum over in Germany. And what you can see is you've got a sole plate and you've got some spikes in the front there. And in terms of running a sprint, the key thing is about force generation and force application, hence the studs and the spikes rather. And even now, you know, sprinters still have spikes, and it's all about force application, less about comfort. If you look about other shoes, here is some ons shoes. We come right to the modern day. In fact, I have a pair of these myself. So there's my old muddy, quite nasty looking ons. And these have these little arches here, which act as cushions and make it very comfortable to run in. These are kind of some of the comfiest shoes I've ever run in. Of course, you've got all sorts of things going on in shoes. And here you've got some Vibrams, they're called 5 fingers. And these kind of latched on to the craze for barefoot running. There was a book came out, said we should all run barefoot. And this was a way of just protecting your feet while running barefoot. And the idea here about improving performance is actually it makes you run on your forefoot. Most of us, or a lot of us like me, are heel strikers. And if you land on your heel, you're losing energy on every impact, you're slowing yourself down. So if you can find yourself landing on your midfoot or your forefoot, you're going to lose less energy because you're not landing on your heels. So that was the idea behind that one. And then quite recently, this is Eliud Kipchoge. Some of you might have seen these Vaporflies, Nike Vaporflies. And these are probably the state of the art at the moment in shoes. Really, really designed to minimize energy loss, maximize comfort. And that's always the balance. When you're doing a marathon, which is one of his races, you want the maximum comfort possible. So you've got a large amount of foam here, particularly in the heel. They're very, very light because if you've got heavy shoes, you know, your foot is a pendulum effectively. If you've got a mass on it, it's a high amount of inertia and you're wasting energy swinging your foot from one step to the next. So you want it to be as light as possible. And the other thing you might have heard about is it has a carbon fiber plate inside there. Not entirely sure of the physics of what's going on. It's not really clear what's going on, but you've got a foam here, which is quite compressible. So it's likely to collapse. So you put a carbon fiber plate in there that's stiff, very lightweight, stops the collapse. So it's not only is it comfortable, it's giving you a bit of rigidity at the same time. And they're very, very lightweight. So I'm going to kind of finish off going down the route of wearables in terms of the physics and the science and how we're using wearables. So this thing here is probably the first wearable that I've come across. It's 1960s. It's called a Mampometer. It was in Japan, and actually it was a pedometer. So it was a pedometer. I don't know if you can see this thing here. It's kind of a little thing. It's got a little pendulum inside, a little ball bearing actually. And as I walk, this rattles up and down, and it's got a little counter on the top, which I can reset to 0 if I want to, and it counts the number of steps. So every time you walk like that, okay, it rocks from side to side and counts the number of steps. And this came from the 1960s, and a doctor of physical education called Yoshiro Hatano. He was worried about people putting on weight in the post-war period. People's quality of life was improving, and that included eating too much. So he was worried about people not doing enough exercise, and this is back in the 60s. So he did an experiment, and he counted how many steps people in Tokyo did. And he realized it was about 5,000 a day. So he just went, you know what, to stop people getting fat, finger in the air, I'm going to make it 10,000 steps. So that's where, if you've heard about the 10,000 steps, that's where that came from. A professor in Japan made it up. Now, it's a good target to have because it does do what it says in the tin. So that's the first kind of meter. And this went like wildfire across Japan. So much so that Mampometer, any wearable is more or less called a Mampometer. So we get to about the 70s and the digital watch came out. Hey, didn't we think we were cool in the 70s with our digital watches with a nice, lovely little red lighting? And there's my digital watch. There's one that I used. It's looking a bit sad now. The battery's all died. And of course, as soon as we got a digital watch, people thought, oh, do you know what? We could use this as a wearable. We didn't use the term wearable, but how could we use the digital watch to measure something while we're doing sport? And the first thing, this was a Finnish company, and this is the guy that created this thing, the sports tester, and it had a heart rate monitor which you put as a strap around your chest. It had 2 electrodes effectively that measured the voltage across your skin. So as your heart pumps, it creates a wave of electricity across your skin, and this measured the electricity across your skin. And then it was transmitted to this sports tester, which became the very first heart rate monitor, which is a polar heart rate monitor. And his name was Seppo. If anyone can say that for me, I have asked people from Finland to say it for me, and even when they've said it, I cannot say it. So this guy, we have to be thankful for this polar heart rate monitor, the very first kind of sports wearable that perhaps we recognize today. Then about 2007, this came along. I've got on my shelf of delights back here, I've got all my old bits of technology. So prior to that, we had some iPods. Then we had a slightly newer iPod with, these had the old wheel on them. And then the iPod turned into a full screen iPod. And then of course, the next thing was to turn it into a phone. So not only is it a thing to listen to music on or take a picture with, it's a phone. And it has all sorts of measurement systems in here that I would have died for 30 years ago. Sensors that we were trying to buy one-offs, and they were costing £1,000 per sensor. So when you consider, you know, a phone now can be a few £100, and the sensors inside those are a few dollars each, a few pounds each. So what can we do with these things? Well, okay, we've got GPS. There's the first GPS. Well, that was my first GPS, a Garmin. And so in the 70s and 80s, the Americans started to put up these global positioning satellites, effectively for the Star Wars initiative. They wanted to wrap satellites around the world. They wanted to start sending missiles at foreign countries, etc. But actually what happened was these 24 satellites in these geostationary orbits going around the world allowed us to track our position to quite an accurate degree, to about, I mean, we can do it for about 20 meters these days. And I have a question actually, how many satellites do you need to see to know exactly where you are on the Earth's surface? There you go, there's a question. So Garmin came out, we've got GPS. Then we've got these MEMS. So these little sensors, these little chips, and these chips have all sorts of things in them. So they've got accelerometer, measures acceleration, a gyroscope, measures rotation, a barometer measures pressure, a compass that measures direction, a GPS that measures position, all on a single chip, a thermometer to measure the temperature of sound, and a Wi-Fi, actually time of flight. Because if you know how far you are from a number of Wi-Fi routers, then you can work out time of flight. And all of these things give you all sorts of bits of information: speed, distance, steps, activity, angular acceleration, angle, altitude, elevation, location, speed, acceleration, lots of different ways of measuring the same thing in terms of speed and position. And these are all based in here. And I'll show you how we use these in our research. So first of all, you've got a camera with a phone with a camera on it. Okay, and as we know now with all the social media, like video is king, really, video rules. And this was a very early piece of work we did with our British diving team, where we set up some cameras by the side of the pool, and we used it to send coaching information back to the athletes so that when they came out the pool at the end of the day, they had these coaching top tips from our top coaches. So this is for our divers. So when they go into the cafe the coach can be saying, look, I've told you this. This is the things I want you to go away and think about. This is what you need to be doing if you're going to get that gold medal. So that's the first place we start is with the video. Here is another way that we can use video. I'll be quiet if you can hear the sound. So in terms of video, the only piece of information you have in video that is reliable is the frame rate. So most of these kind of cameras are running at 30 frames per second. So if you count the number of frames, you can count time. So here what we've got is we've got a very simple image processing algorithm that we've created to use on video coming off TV feed, and we can count the number of steps. And because we can count the number of steps and we know the time, we can look at the rate. So here you've got Usain Bolt. He's just won the World Championships and he's got very long legs. So he's got a low stride frequency of about 4.4 hertz. You've got here Justin Gatlin, he's just been beaten. So he had a very high frequency of 4.8 hertz, 43 steps. And third place was Andre de Grasse, 4.8 hertz, 45 steps. So this is the kind of information that coaches use all the time when they're training their athletes. What is their stride length? What is their stride frequency? It's very, very important. And video contains that information inside it. And all we've done is I've taken, I can't remember if it was a physicist, I think it was a mathematical engineer was the person that did this, who created this image processing technology that tracked the footsteps of these athletes. So, okay, we can go one step further. Here's at Roland Garros, the French Open. This is just on a training day. So what we want, the task here was, how can we track an athlete, the footsteps of these tennis players on a tennis court using one camera? Only one camera we're allowed. So the camera's over there, so you can just about see in the trees, there's a little tripod with a camcorder over there. And this is the view from that camcorder. And this is them setting the camera up. So here you've got someone, and he's got a large ruler going down to the ground. And this is the origin of a bit of analysis we're going to do. So what you can see is we've got lines on the tennis court. We can see we've got a net there. And we've got now what is going to be an origin. So if I click the picture, we do our little bit of analysis. There is our three-dimensional domain, and we know it's in 3 dimensions. This is the plane of the tennis court, and we've measured those distances. So we know exactly where that plane is, and it's in the XY plane there. The normal to it is the Z plane. And yet we've got a 2-dimensional image. We have a 2-dimensional image and that has an XY plane to it. So you've got lots of pixels across this image, and we need to convert those pixels into this 3-dimensional domain. Now, where we can do it accurately is in this floor plane. Anywhere away from that floor plane gets less accurate, but we can do it in that plane of the tennis court. And what you can see here is you can see these circles and you can see these arrows. And if you've ever taken a picture with your phone, out at the edges, people's heads kind of get all kind of distorted and out of shape. And that's because of something called spherical aberrations coming from the lens. And these arrows tell you how big the errors are likely to be in different positions. And you can see that the arrows are very small. In fact, you can't even see any arrows in the middle here. This is always the best place, the least distorted place in the center of the lens of the camera. And basically what's saying is, don't take any data out here, don't take any data, you're going to have really poor data over here, but over here it's going to be okay. So now my mathematician takes this data, transforms the information from the 2-dimensional picture into 3 dimensions, sets up some image processing, sets the algorithm going, and here you can see an algorithm. This is I think this is Federer. This is Federer, an event. What we're trying to do is we're trying to track Federer's feet. That's what we're after. We've got a pseudo center of mass. We're kind of trying to guess where his center of mass is. So that yellow dot is his center of mass, and these 2 red dots down here at his feet or where his feet touch the surface. And you can see over here, you can see a green line, which is tracking with a plan view, looking down onto the tennis court, where the player goes, and then where the footsteps go. And that was a piece of work we're doing with the International Tennis Federation, looking at court surfaces, looking at slips, looking at injuries, and so on. So the question was, how can we track this player using a single camera so it can tell us when he slips and why he slipped? And that's the kind of outcome there. We use the same piece of technology as a coaching tool for our local runners. So hopefully you saw running past was, hang on, let's do it again, was 2 runners. The faster one is actually the one that wrote software, and you can see 4 steps there, and there is our little calibration plane there, the little green lines there, and up here you can see step length, sorry, 2.24 meters, step time, 0.255 seconds, speed, 8.8 meters per second. That's pretty fast, actually. That's pretty good going. And there's our coach looking at some of those images, telling that particular athlete what he should be doing to improve performance. And then we've also taken that same piece of technology into a hospital. This is the Royal Hallamshire Hospital in Sheffield. And this is where we start thinking about well-being of the general population and not just performance of athletes. So we're tracking, this is the consultant, and we're tracking that consultant's feet across the floor here. So where are the contact points there? And if we look on the next slide, what you see is when we start looking at patients, patients have a step length of about 60 centimeters, 600 millimeters, but healthy people have a step length of over 700 millimeters. And that's because, you know, people who are less healthy might have some problems with gait, kind of do a little bit of a shuffling kind of thing. And then you've got step frequency here. So quite a high step frequency for patients. So again, a bit of short and shuffle. Healthy patients, long strides, low frequency. It's kind of Usain Bolt kind of strides. And then when you look at the walking velocity, you saw some calculations in the tutorial before this. You can work out, if you know step length, which is the wavelength effectively, and the frequency, you can work out the velocity. There is your velocity, 1200 millimeters per second for the patient, almost 1400 for the healthy person. A single camera in a gait lab, in a hospital, where you don't have time to take measurements, and actually you can't take measurements. It's just not possible to attach things to people, particularly if they're old. So that's the transfer of these ideas into useful things for wellness. Now, in the laboratory, we have a motion capture system where we have cameras around the laboratory, and we have 32 of them, I think. And you have a person with lots of markers on. You can see these markers, so you can see the kind of shining brightly. They're like tiny balls with reflective tape on them, a bit like you see on people's jackets outside. And those markers, we track those markers using all these cameras, and it's really quite expensive, maybe £250,000 worth of camera system. If we use that camera system, we can track the back, the sacral point here, sorry, that point there, we can track how it moves in 2 dimensions, the vertical and the medial lateral. So medial lateral is this plane, vertical is obviously this plane. And if I was to run, and actually you might want to, if you focus on the helmet of the spaceman here, then if I run, okay, what you'll see is you'll see me going up and down, vertical movement, and you'll see me going side to side at the same time. So as I'm running, I'm kind of doing this. And what it creates is it creates this lovely butterfly pattern in this plane here. So that's what you get from a £250,000 motion capture system in a laboratory. Now, we can also attach a sensor, kind of the size of this kind of thing, onto the back, tape it on, and it's taped underneath there, and you get that image. So you can do the analysis. Okay, and what you see is, look, there is the inertial sensor, which is this thing. There's the complex camera system, and you can see this same butterfly pattern. So what we can do, we can take a single sensor and do the similar analysis wherever we want. It doesn't have to be in the laboratory, it can be wherever we want. And actually, we're less interested in the values because we know there's errors, we know they're not exactly the same. We're less interested in the numbers themselves, more the pattern, the shape. So it's now a pattern recognition problem rather than an absolute numbers problem. And here you've got someone who's got an ACL tear, an anterior cruciate ligament. Someone in the audience there, it's probably hurt their knee. It might be an ACL tear. It's common in footballers. And what's happened here is it's changed that pattern of that particular athlete. And then with this particular athlete, again, this is just using the single sensor. I don't even know what these are. Right Lisfranc sprain, left hip labral tear. And this player was saying, near return to play. I can return to play. I'm fine, coach. Coach, I'm ready to get on the pitch. I'm ready to work for you. And actually, you know, that is not true at all. So the idea here is how can we use sensors to monitor performance, but also to monitor injury? And this could be used both in athletes, but also in the general population. So the future, how am I doing for time? Oh, I've run over time. Okay, I will finish off. The future, sensors, they're coming out as left, right, and center. So you got all sorts of things. And here, in terms of, you don't have to wear a heart rate monitor around your chest anymore. You can wear something like that, and you can see I've got a watch there with some lights in the back, and that's monitoring the blood flow in my wrist. You got something there, which is just a stick-on, measures how dehydrated you are, and you got something there that fits in a gum shield, and it's measuring blood lactate, something we really, really want to be able to measure. Do you know what? I'm not even going to go there. Transcranial magnetic stimulation or graphene, we can talk about that. Really, the future, I think, is that we're coming into a world of data. And for those of you might know about parkrun, parkrun is an event. There's thousands of them across the country. They're in a park near you, lots of numbers of people doing the free weekly timed 5 kilometre on a Saturday morning. Simple technology. It's a barcode. It's a scanner when you finish. You queue up to get your scan, and that's key because it gets the socialization going. And you end up with some numbers online telling you your position and your time. And then numbers, huge, huge numbers, 10,000 people a week, new parkrunners every week, 500,000 new parkrunners every year. So we're ending up in the world where we're getting lots and lots of data, and we can do lots and lots of analysis of that. And we can both improve performance, but it can also encourage people to do physical activity. So how can we use technology to improve performance? What technologies we use? Well, we use materials. We use things like moments of inertia. We maximize those or optimize those moments of inertia. We optimize the amount of energy that goes into whatever the performance is, whether it's running, whether it's hitting a ball, whether it's flying through the air on the bike, and we minimize the energy loss. That's effectively all we do in sport. Do they work? Absolutely. I've shown you some examples there. Is it cheating? Again, actually, it just depends upon the rules. The physics allows you to do anything within the world of physics. The world of sport is one small kind of subset of that. So a little bubble inside, and that bubble moves around as the rules change. So is it cheating? If it's inside the rules, no, it's not. If it's outside, yes, it is. Right, I will finish there. So that's a book I have got out. It's around here somewhere. I would ordinarily have had a box full of them at a lecture, so I've still got a box of them. They're here in the office. And if you want to watch a video, there's a video online called The Equalizer, where we've got Paul Biederman here, who you saw earlier on, Andre de Grasse, who you also saw on there. This is online. I think it's on Amazon Prime, where you can look at the role of technology in sporting performance. And at that, I will leave it. Thank you very much. Maria, I can't hear you.
Right, thank you very much. At this point, if we're live, you get a huge round of applause, and we don't. Instead, you're getting loads and loads of people saying thank you in the chat. There was a bit of debate about, some people said 3 satellites and somebody else said you need a 4th one to do time. So I think it's 3 for triangulation, and it deals with its own. You do need 4. Yeah. Okay. So
and it's not about time. It's not about time. It's about positioning. If you use 3, you get 2 answers. I need a 4
yeah.
to work
Okay.
out which answer it is.
Right. Yeah. Okay. That makes sense. So it's a simultaneous equation.
It really is. Yeah. Yeah.
Yeah. Okay. Right. Okay. We are a bit over time. If there are any questions, stick them in the chat real soon. But actually, we've done quite a lot of these things now, and to get a big wave of people saying thank you like that is quite special. So, and I it's close to my heart, these kind of subjects. So I really enjoy it, and thank you very much.
Yes.
Yeah.
My apologies for taking so long. I was far too many slides. Sorry.
But it's so much interesting stuff. That's why you get it. Right. I think we are out of time, and we're not getting loads of questions coming in. So,
well, listen, what I will do is, yes, I can understand people might go, oh my God, there was so much there. I have no idea what to ask. And actually, I do get lots of people coming. If anybody wants to send me an email, so there's my email address. Hopefully you can actually read it. That's s.j.haake@shoe.ac.uk. So do send me an email. I've got a blog on there. I haven't added to it very much, but it gives you an idea of the kind of things that are going on. Do look up the video. So contact me. Yeah, and so on. And buy my book. Buy my book. It's out there. It's come up to Christmas. If you've got anyone who likes sport and technology, it's a nice little Christmas present. There you go. Quick plug.
Yeah, excellent. Right. Okay, I think I'm going to suggest that we finish this one there. This will be recorded and available to watch after the date. So, yeah, okay. Thank you very much indeed.
Thank you. Okay. Sign off. Have a good night, everybody.
Yeah, okay. Bye.
Bye.